In this lecture, we're going to learn about strain displacement analysis of beams. Now, there's going to be some restrictions on what we're going to discuss. Right now, we're only going to be looking at pure bending, but a little bit later on, we're going to relax that and allow for shear forces in our beam as well. We're going to have a beam with a constant cross-section. Doesn't taper down or anything. It stays the same dimensions all the way across the length of the beam. And our beam is going to have a vertical line of symmetry. So I've drawn a couple cross sections here that have vertical lines of symmetry. Of course, our rectangle, our T-beam, or if we have an I-beam, or a circular cross section, these are all examples of cross sections that have a vertical line of symmetry. Now, the beam theory that we're going to develop is something called Bernoulli-Euler beam theory. So you may hear that term in some other courses or if you do your reading. So we're talking about how beams deform and move and displace under loads. So let's start off with just a sketch of a beam like my yardstick that I've talked about before and after it's loaded. So my yardstick is sitting here. I'm going to draw it a little bit bigger, maybe than I have in some other pictures. Try to get that straight. And there's no load applied to it right now, and its length is L. And I take this and I can identify a couple points, maybe P and Q on the top, and R and S on the bottom. So everything has the same length. P and Q is the same length as R and S before I put any load on it. Now I'm going to apply a bending load. And like my yardstick, you can do this with a ruler if you have one. We can bend it, and when it bends, it's going to change shape. Let me draw that over here. Try to exaggerate this a little bit. Okay, so there's my bending moment. If you notice, that bending moment is in the positive direction for an internal bending moment. It's putting the top of the beam in compression. And because the top of the beam is in compression, the points on the top actually get a little bit, the line segment on the top actually gets a little bit shorter. So let's call this P star and Q star because these points have moved. And on the bottom is in tension, so the bottom line segment stretches out, maybe R star and S star. So the change in length of the line segment that was initially from P to Q gets a little bit shorter. It's less than 0. And the line segment, I'm going to leave a little space here for a reason, the line segment from R to S stretches out and it gets a little bit longer. Well, that means that we have a compressive strain on the top, and we have a tensile strain on the bottom. Negative and positive strains on the top and on the bottom of the beam, respectively. Now, there's something else that happens that we kind of have to think our way through, kind of reason through this. If the top gets shorter and the bottom gets longer, we're transitioning from negative strains to positive strains. If that change is smooth, and it will be, there will be some position on that beam where there is no strain. So let's see. It must have come from some point over here to here. Let's call that T and U. If it moves to T star and U star, now dash that line in. So it's such that the change in length of the line segment that was originally from T to U is exactly equal to 0. And so that means the strain along that line segment is going to be 0. This line segment is going to be a very special place for us, and it has a special name. It's called the neutral axis of the beam. We are going to learn, and see why this comes about, we're going to learn that the neutral axis of the beam is going to be located at the centroid of the cross section as long as we have linear elastic material behavior. And we'll talk about what all that means coming up soon. But for now, we want to know that that special name for the place where there's 0 strain in a beam when it's being bent like this is the neutral axis. And we're going to abbreviate that sometimes as NA. Now there's a few more observations that we can make about what happens when we bend this up. And for that, I'm going to clear this page off and make a new page. Right, so some additional observations that we can make is that not only do we get a neutral axis when we look on this beam in a side view, but when we look at the beam in 3 dimensions, we have an entire surface in which the strain in the axial direction, the longitudinal direction of the beam, is equal to 0. And that's called the neutral surface. So that's a plane of epsilon x equal to 0, where the x-axis goes down this way. Now the neutral axis is going to be kind of special to us, and for that reason we're going to start our y-coordinate coming up from the neutral axis. And to keep a right-handed coordinate system, then our z-axis will go this way. So we have the neutral axis, we have the neutral surface. Something else we can make an observation about is that plane cross sections remain plane under loading. Now this seems like kind of a weird thing to say, but all that means is if we can identify a vertical plane in this material for a cross section, I'll sketch that in this green. When it gets loaded, it still, on a side view, looks very straight and flat. It doesn't do anything weird. I'll draw this and I'll erase it. Use a different color. It doesn't do something like that. Okay, it just doesn't do that. It just stays straight and flat. So that's what they mean when you see this phrase, plane cross sections remain plane. The other thing that happens, and this isn't maybe as easy to see, but it's a good assumption we can make for pure bending of beams, is that all the beam cross sections point toward a common center of curvature. So if this beam is being bent, it actually gets bent into a circular arc. If we were to extend these cross-section lines anywhere around here, they would all point to the same common center of curvature. So let's do this. The cross-section planes point toward a common center of curvature. Now, as we mentioned at the beginning, these assumptions and restrictions make up what's called Bernoulli-Euler beam theory. Now on the next page we'll get into some more details about finding the strain in the x direction for a beam that gets bent in this way. Now we've mentioned about the strains on the top and bottom surface of the beam, and that the strains in the longitudinal direction were 0. But we want to dig into this a little bit more, and we want to get an equation that will tell us how the strains change from the top to the bottom of this beam. So in order to do that, I have this sketch that I have on the right side of the screen where it's the beam before it has any loads applied to it. My neutral axis is dashed in there, and I have a couple points on the neutral axis, points A and B. And P and Q lie some distance above that. I'm going to call that a distance y above the neutral axis. Now initially they're separated by a short distance, delta x. And like we tend to do, we're going to take that delta x distance and shrink it to 0 to get the strains at a point. But for right now we're going to leave them separated a little bit and just call that distance delta x. Now when I take my beam and bend it, we also talked about how it bends into a circular arc with a common center of curvature. I want to exaggerate this a little bit. So I'm going to draw this next picture kind of large in comparison to the picture that I have on the screen right now. And it's a little difficult to get good looking arcs, but I'll try my best here. Okay. So here's my common center of curvature right here. And my point A and B, said I wanted to exaggerate them a little bit. They're on the neutral axis. So they're on this arc that's dashed in. Since they move, I'm going to call them A star and B star. Now although they move and turn into an arc, they don't change their distance in between them. So the arc length is still an arc length of delta x. Now that is an arc length, so there's an angle that we can define. I'll call this angle delta theta star, and a distance from the center of curvature to A and B. And this is going to be an important term for us. I'm going to call this distance rho. It's the radius of curvature of the bent beam. And rho is defined as going from the center of curvature down to the neutral axis. Let's write that down over here. And we do need to keep that in mind, that it does go to the neutral axis. Now we talked about how when we put a positive bending moment on our beam, the top goes into compression and gets shorter. And anything on the top half of the beam gets shorter as well. So these points P and Q, they get a little bit shorter than what they used to be. Their new positions, we'll call them P star and Q star. And they go along an arc that has a length something less than delta x, what it started out with. Let's call it delta x star. Now the arc length delta x can be found by the radius of curvature times the distance from the center of curvature, the radius of curvature times the angle enclosed, so it's rho delta theta star. And then that means that this distance delta x star is going to be rho minus the distance y times the angle delta theta star. And because that point P and Q is a distance of y above the neutral axis, we have to subtract that off of this radius of curvature term in order to find that arc length. Well, the strain between P and Q is the change in length divided by the initial length. So we have the final minus the initial length divided by the initial length. And we can do this, write this now in terms of the angle in the radius of curvature terms. Delta x star is rho minus y times delta theta star minus delta x is rho delta theta star divided by delta x, which is rho delta theta star. And we see from this equation that the delta theta star terms do drop out from each of these terms. We have a rho minus y on the top, but we have a minus rho as well. And so the positive and negative rho's cancel out, and we're left with the strain between points P and Q as minus y over rho. And even if we shrink delta x down to nothing, we still end up with this term. The strain in the longitudinal direction of the beam is depending on the distance we are away from the neutral axis, divided by the center of curvature of the beam. If you have a small radius of curvature, you're really bending the beam up into a very tight arc. You will get a lot of strain. If you have a very flat beam, completely flat, you'd have an infinite radius of curvature, and then you'd have zero strain in your beam. Of course, if you put any loads on it, you're going to bend it some, and you'll get different levels of strain that way. But the other important thing to note about this equation is that this y is a variable. It goes up to the top of the beam, and it goes down to the bottom of the beam. So here, this is maximum positive y, and down here, this is maximum negative y. So the strains are going to be the biggest on the outside edges of the beam. Not only that, because this is y to the first power, there is a linear strain distribution in our beam when we have it bent with a bending moment. That's going to be very important. I'm going to say that again on the next page, but I'm also going to make a sketch to emphasize this equation. Epsilon is equal to minus y over rho. Alright, so now I'm showing a side view of my beam, and I have my bending moments applied to it in their positive direction. Positive bending moment puts the top of the beam in compression. I have my neutral axis identified. My y distance goes upward from the neutral axis, and I'm going to sketch what's called the strain distribution in the beam. Depends on y, so that means when y is equal to 0, I get 0 strain. When y is equal to the maximum positive value, I have the negative sign in the equation, which causes a compressive strain on the top. When y is on the bottom, I have a negative y value, and the negative in the y and the negative in the equation work together to make a positive strain on the bottom. And the distribution from the neutral axis to the edges of the beam are going to be linear. So as I go further from the neutral axis, I start to get bigger and bigger values for the strain in the axial direction. So this sketch is the strain distribution in the beam. Now if we have a linear elastic beam, and we will also have a uniaxial stress state in this case, we can use 1D Hooke's law to relate stresses and strains. So sigma is equal to E epsilon. So the stresses in the beam are going to look like minus E times y over rho. And so if I wanted to sketch the stress distribution in the beam, it would look exactly the same as my strain distribution. maximum compression on the top. When I have a positive bending moment, maximum tension on the bottom with that positive bending moment. So this would be the stress distribution. Now the beams that I've drawn here, I'm assuming that the neutral axis is in the middle of the beam, halfway up. In some cases, it won't be. And we'll find out later that it's going to be located at the centroid of the cross-section for elastic bending. So if we had a T-shaped cross-section, it's quite possible that our neutral axis would be skewed toward the top of the beam. In this case, the biggest magnitude of stress will be on the bottom edge. The slope is the same. It's still first order in y with 0 at the neutral axis, but with a positive bending moment, the biggest magnitude of stress and strain will be on the bottom edge because we have a further distance to go to get down there. Now if we reverse our bending moment, then we reverse the stress distribution and have tension on top and compression on the bottom. Now the homework problems in this homework set tend to be fairly contrived. And that's because we're using these formulas that have the radius of curvature term in them. Let me clean off this page and let me draw a sketch. So the problems in this section tend to be something where you have a pulley or a drum and you take some metal strap and you just run it around this pulley. No, not making a perfect sketch here, but kind of get the idea. I'm going to exaggerate this. And let me clean this up just a little bit. And they'll ask you to do something like find the maximum strain and the maximum stress in this beam or band or whatever it is that's being wrapped around this drum. And they'll give us the radius of the drum. So if we want to find the strain, we know the strain is going to be equal to minus y over rho. But we have to be a little bit careful. The radius of curvature goes from the center of curvature to the neutral axis. And in this case, that means if it's a rectangular cross-section, and they usually give that to us, that means the distance here is a little bit greater than r. So in this, rho will be equal to r plus h over 2, where h is the thickness of this strap. Now the y distance is the distance from the neutral axis to the outer edge of the strap, and so that will be the height h over 2. So our strain, epsilon, in magnitude is going to be equal to half of the height divided by the radius of the drum plus h over 2. And if we want the maximum stress, then we just take that number and multiply it by the maximum strain times our modulus of elasticity. So we have E times h over 2 divided by r plus h over 2. And all these problems in this section are kind of like that. They're very contrived, and the reason why is that it's kind of difficult to determine your radius of curvature. So let's write that down. Rho is hard to measure. And so in the next lecture, we're going to get rid of that rho term, and we're going to replace it with a term that has the bending moment in it, the load, and the moment of inertia of the beam's cross-section, the I. And we talked about that in one of the previous lectures recently. Now, one thing I do want to emphasize again is the stress distribution in a beam and bending. I will often ask that on an exam to have students sketch that for me. And again, it is a linear variation coming up from the neutral axis, and the arrows depend on which way the moment is going. But this would be a picture of the stress distribution. Okay, so you make sure you understand and know what the stress distribution of a beam is before our next exam.